Today, the first speaker is Vera Traub from ETH Zurich. She's an associate professor there, and her main areas are combinatorial optimization and approximation algorithms. Prior to joining ETH Zurich, she has been a professor at the University of Bonn, and before that, a postdoc in Zurich. She obtained her PhD in 2020 from the University of Bonn. And for her research, she received several awards, including the EATCS Distinguished Dissertation Award, Miriam Mirzakhani New Frontiers Prize, and the Heinz Meyer Leipzig Prize. So today she will be talking about unsplittable cost flow for unweighted error-bounded variance. And if you have any questions, feel free to write them in the chat and we will relay them to the speaker.
Okay, yeah, thank you very much for the introduction. So today we'll talk about some joint work with Chaitanya Swamy, Laura Vargas-Koch, and Rico Zenklusen, and this will be about unsplittable flows. And let me first start by introducing the setting, and let's first start by looking at the usual network flows that we all know. And so the setting here will be that we are given some directed graph G with vertices and arcs or edges. We will look at a single source setting here, so we'll just have a single source vertex S here in this picture, and we have a set of sinks T. These are like these squares in the picture, these are the sinks, and every sink comes with some non-negative demand. So the first sink here is demand 1, the second sink demand 5, and the third sink demand 2. And now what you can see here in orange is a fractional flow sending the required demand from the source to each of the sinks. So we are sending whatever demand we need. And like one way of describing the set of all feasible flows here, so this is the set Q here, is we can describe this as a polytope. So we have basically a variable for every arc, which is non-negative. And the constraints that we have is that if we look at any vertex and we look at what's the outgoing flow minus what's the incoming flow, then we are sending a demand of dV into each of the sinks. So that's what this first constraint is saying. And then out of the source, the amount of flow that we are sending is just the total sum of all the demands that we are sending. And for all the other vertices, just the incoming flow should be equal to the outgoing flow. So these are like classical network flows. This is what we call a fractional flow. And now we want to look at unsplittable flows. So here in this example, you see an unsplittable flow Y here. And so let's see, like, why is this called an unsplittable flow? So we say that Y in Q is an unsplittable flow. So Y is in Q, that first of all means it's a flow as we've seen it before. But then in addition, we require that Y is sending the flow to each of the demands along a single arc. So for example, here in this picture, we are basically sending 1 unit of flow along this red path. We are sending 2 units of flow along this green path, and we are sending 5 units of flow along the blue path to the blue terminal. So, but the important thing here in unsplittable flow, in contrast to a general flow, is that we are sending the flow to a single source, single sink, all along the same path, and we're not allowed to split that up. So what this means formally is that we can write Y as the sum over all the sinks, and then we simply sum up dt times the incidence vector of some path. So this is here is the incidence vector of some ST path, PT. So this is what we would call an unsplittable flow, in contrast to a general flow. And now there are some classical beautiful theorem about unsplittable flows, and this is due to Dinitz, Gag, and Goemans already, more than 20 years ago. And what they proved is that whenever we have any given fractional flow, then we can find an unsplittable flow which has satisfying the same demands in the same graph, which has the nice property that I can guarantee that for every single arc in my network, my unsplittable flow will not send will not send much more flow than our given fractional flow. Namely, it will not send more than the fractional flow, what the fractional flow was sending, plus d max. And d max, this is just like the maximum over all demands. So this is just the maximum over all t and t dt. That's the maximum demand. And this kind of violation is actually necessary, as you can see on a very simple example. So even if I just have one terminal and my graph just consists of a bunch of parallel arcs, it could be, maybe we have something like dt equal to 1, but my fractional flow could now send an epsilon amount on each of these arcs, but then in my unsplittable flow, I will actually have to decide for one of the arcs. And so no matter for which arc I will decide, I will basically get a violation of dt, or dt minus epsilon. So basically this violation of d max is unavoidable. And what they proved is, that one can actually always achieve this, having a violation of not more than d max in terms of upper bounds. So this is, a beautiful theorem by Linhares, Skutella, and Goemans. And there are, a couple of conjectures that are all still open around in this area of unsplittable flows. And so one conjecture is due to Goemans. And what he was asking is, if we have basically the same setting, but we are now not just caring about, but now in addition, we also have costs. So every arc now has a non-negative cost. And if we are asking, we again want to achieve the same thing. We want to get an unsplittable flow where, the flow in every arc increases by at most the maximum demand. But what if I have, in addition, want to have the property that my unsplittable flow is not more expensive than my fractional flow? Can I still achieve this? And the conjecture is that this is possible, but this is in fact widely open. And then there are some more conjectures. This one is due to Morell and Skutella, where they asked, okay, now we will actually assume that from now on we will assume that our graph G is acyclic. In the previous setting, this was somehow without loss of generality. Here it will be important, but just even for the question to make sense somehow. So what we'll ask here is that if I'm basically asking, this conjecture is saying basically I want to achieve the same as this theorem by Linhares, Skutella, and Goemans, where we said, okay, the unsplittable flow on every arc should not be more than the fractional flow plus d max. But now I could also say, okay, here we're saying, okay, the unsplittable flow should be not much more than my fractional flow, but maybe I also want that my unsplittable flow is not much less than my fractional flow. So basically they said, can we always find a fractional flow that doesn't deviate, or can we always find an unsplittable flow that doesn't deviate from my fractional flow by more than d max? And so they also proved that if you only want to have these lower bounds, then you can achieve this. And I mean, Linhares, Skutella, and Goemans already showed that you can achieve this if you only have the upper bounds, but it's widely open whether you can achieve both things simultaneously. And they also, this conjecture is also related to some open questions in scheduling and also to some problems on discrepancy theory. So this is a quite relevant thing, but it's widely open. Yes. And then they also had a third conjecture, which is basically a stronger version of conjecture 1 and conjecture 2. So now we do have the lower bounds in addition to the upper bounds, and we also have the cost, this costing. So we also wanted our unsplittable flow is not more expensive than our fractional flow. And this conjecture 3, this is like the strongest conjecture, which would imply the other two conjectures. So these are three well-known and widely open conjectures in this area. So what is known about these conjectures? In general, as I said, it's widely open, but they are known to hold in some special cases. So for example, we know that the conjectures are true when all the demands are multiples of each other. So if they have a very particular structure. We also know that the conjecture is true for serious parallel graphs. And then it's also true for planar graphs or even bounded genus graphs if we allow for a slightly larger violation. So if we allow a violation of 2d max instead of d max here. But actually, like, yeah, this 2 is not very particularly important. So even if I just want to get any constant times z max, then all these conjectures are widely open for general graphs. So there's not much known about this in general graphs, but we do know that they are true in these special cases. Okay, so now what is our result? What I want to talk about today. So what I want to talk about today is that here are again these 3 conjectures. What we've been showing is basically that if in the first conjecture, like the conjecture by Goemans, which was about adding the cost condition here, that if we allow a violation of twice the max instead of just the max, then conjecture 2 implies conjecture 1. And similar for conjecture 3, if we allow a violation of 2d max instead of just d max, then conjecture 2 also implies conjecture 3. So basically what this says is if we can do lower bounds and upper bounds simultaneously, then we get the cost version, like these extra costs here, we get those for free. We don't we can prove a statement without cost, and then we will get this cost version for free. That's basically our main result, what we prove. And in fact, we prove our result in a much more general and abstract framework, which I will introduce next. And then these kind of implications, they just follow as a simple special case of that. So, but like the main application of the general theorem that I will show you is like really these implications between these different conjectures, which have been around in the area for a while, and where this connection was so far not known. Okay, so now let me in the next part introduce what's the general setting and like the general result that we actually prove, which then implies these implications between these conjectures as a corollary. And this more general setting, I should say that our work here generalizes also earlier work by Linhares and Swamy from 2018. This was in the context of degree-bounded spanning trees, but we generalize their results here significantly. So what we do is, in our general setting, we will not talk about flows or anything specific to flows anymore, but in fact, all what we prove here works in a much more general setting. So the setting is as follows. So we are given some Q, which is in general just any polyhedron. And in our setting, this is just a Q that we've seen before. So this is just the set of all fractional flows. Then what we are also given is we have some subset Z of Q, and this is what we call like the feasible solutions. And in our case, this would just be in our application. For concreteness, this would just be the set of all unsplittable flows. This is what Z would be. And then we will also have in our general setting a subset of N. So this is what R will be called the error body. The role will become clear in a moment. This R is in general just some convex body which is containing the origin. So this is containing 0. And in our case, R will just be equal to the cube from minus d max to plus d max to the A. So this will just be our error body R. And so really what we will assume is for our main result is that what we are given is a so-called phase-preserving rounding algorithm. So let me explain what this means. So this is what we assume to be given as an oracle. And what this oracle will do for us is that if we are given x and q, So in our case, if we are given some fractional flow x, then it will return z, a feasible solution z. So in our case, it will return an unsplittable flow with the property that z minus x is contained in R in the error body. So in our case, this means that, like, if I look at the difference between my unsplittable flow and my given fractional flow, that this is not too large because it should be inside R. And in fact, like that we can get such a thing, like this statement is really what our what our conjecture 2 is giving to us, is promising exactly an oracle for this. Now there's one thing that I should still add here. So I said this, I want my rounding algorithm to be phase preserving. So I will actually need one additional condition. And this is that Z is contained in the minimal phase of Q containing X. So just to give you a picture what this would look like. So if I have my polytope Q here, and then perhaps my point X is somewhere here, then I will look at the smallest phase of Q that contains X, which would be this one in this case. And then I want that Z should somehow also lie within the same phase. So that's the condition. And in general, you could now say, okay, conjecture 2 doesn't promise me anything about anything that has something to do with being phase preserving. But the nice thing is that if we look at our particular choice of Q, this polyhedron that we were looking at, then this condition of Z being in the minimal phase of Q that contains X actually just boils down to saying that Z does not use any arcs where x of a equals 0. So this just says our flow, our unsplittable flow shouldn't use any arcs that our fractional flow did not use. And this is in fact actually a trivial condition, because if I have an arc where the fractional flow was 0, I could just delete this arc and then apply my oracle to this updated graph. So this is actually in our particular application for these flows, this is actually this condition is we can assume this basically without loss of generality. In general, of course, if we want to apply this more generally, then we need this condition actually. Okay, so this is the setting. So we have this polyhedron, we have the set Z, we have this error body, and what we are assuming it to have is this, to be given is this phase preserving rounding algorithm. That's what we are given as an oracle. And now, let me explain you what we will now do. Our result is basically, I will give you a very simple algorithm consisting of just 2 steps. But then I will actually prove to you that this algorithm will actually do what we want. So here, let me say what's the algorithm. So basically, we have our Q subset Rn, that's a polyhedron. We have Z subset of Q, and we have our error body, our subset of Rn, which is convex with 0 in R. Okay, and we are given this basically this FPRA, our phase preserving rounding algorithm. So really, we don't need any explicit representation of Q or Z or R or anything. We really just need this phase preserving rounding algorithm. So here's the algorithm that we will now apply. So the algorithm is very simple. Step 1 is the following. We find an optimum solution y star to the problem of minimizing C transposed y such that y intersects y. So y is an element of Q intersected x minus r. So the only thing that we kind of need is that this about this error body is that this is actually like a problem that we can solve. That's the one thing we need. And just to be clear here, what do I mean with x minus r? So this is just all the set of all vectors x minus r such that r is in the error body. So this x minus r here is in the sense of a Minkowski sum. And our second step is that we apply our phase-preserving rounding algorithm to y star, and this will give us a vector z. And now what's the theorem that we prove, and this is a theorem about this algorithm. What we prove is that we then have C transpose Z, so the vector Z is the vector that we output here. Say this vector is no more expensive than the vector than X, so C transpose X. So we start off, basically, we also have we have this X in Q. So this is basically, if you want to think about concretely about flows, then X is our fractional flow. And then we say our unsplittable flow that we output is not more expensive than the fractional flow that we put in. And we have the property that Z is contained in X plus R minus R. So Z is not too far away from X. And just to be clear here, so R minus R is not 0, but this is just the set of all vectors that I can write as X plus R1 minus R2, such that R1 and R2 are both vectors in R. So this is again in the sense of a Minkowski sum. And basically, if I apply the theorem to our particular setting about unsplittable flows, then this will exactly kind of give me my conjecture, because I now get this nice cost bound that I wanted, and because I have this R minus R here, so I basically have this R appears twice. That's why I now get kind of twice the violation, on each of the arcs instead of just once the violation that I had in my original error body. Okay, so this is our general result. Let me now just very briefly try to see if I can still show you the proof. So the proof is basically just one picture. So it just will fit on the slide. Like explaining the statement probably took me longer than proving this. I here have the algorithm again, and here's the theorem. So how does this work? So I start with my point X. That's kind of my fractional flow. Now I found this vector y star here. That's what I've seen here. This was the output of a minimization problem. Maybe y star is lying here. It could be anywhere in this polytope Q, but just as an example, maybe it lies on this face. Now my phase-preserving rounding algorithm will give me a point Z, which is lying on the same minimal face. So what do I know about these vectors? So first I know that going from X to y star, this will actually be in minus R. This is because y star was contained in Q intersected X minus R. So going from X to y star, the step I will take will be something in minus R, and I will certainly stay within Q. I can also say that going from y star to z, this will be in R. This was basically the condition. That's how the error body was chosen, such that the FPRA, our phase-preserving rounding algorithm, when going from y star to z, we move away by some vector that is in R. And now I can use that this whole thing was phase preserving, and I know that if I go from y star in kind of not in the direction of z, but in the opposite direction, I can go at least I can take some small step in the other direction. So I can go here in direction minus epsilon, go here in the opposite direction by an epsilon fraction of what I went in the other direction, and I will stay within the polytope. And I will call this point here y bar. And now I observe that if I look at y bar minus x, this is actually a vector in minus 1 plus epsilon times r. So this is basically because from x to y star, I'm going something within minus r, and then from y star to y, I go again, take some step within minus epsilon r. So minus r plus this minus epsilon r. And this gives me that this difference is actually in minus 1 plus epsilon times r. And now here's the trick. Basically, what we will do is we'll look at the point y hat, which we define as x plus 1 over 1 plus epsilon times y bar minus x. So basically, I look at this line between x and y bar, and I'm not going all the way to y bar, but I'm just going 1 plus 1 over epsilon fraction, and this is y hat. And so the key observation now is that we have that y hat is actually in Q intersected x minus r. So this is just basically because this difference here was in minus 1 plus epsilon times r, and now I'm just actually going a 1 over 1 plus epsilon fraction. So this thing here cancels with this. So what this means is that y bar was actually a candidate to choose in my optimization problem here. So this implies that C transposed y star is at most C transposed y hat. And this tells me that if I look at this direction, what this tells me is that the cost is non-decreasing. And now the cool thing is that what I can see is that if I go from x to z, this is actually parallel to this direction. So also here the cost is non-decreasing. And this gives me this nice cost bound here, which is actually like the difficult part of the theorem. This other thing is fairly straightforward to observe. And this is actually already the full proof of this kind of more general setting. But then like if we apply it to a concrete setting, then this application, what we get is these implications between these conjectures, which are all still wide open. So these are very interesting open questions. Can we prove these conjectures even if we put just any constant in front of these Dmax things? This is all widely open. But at least we now know that these conjectures are related. And somehow if we prove the second conjecture where we don't have any bounds on the cost, that then we get these cost bounds somehow for free. So there is we have this relation between these different conjectures. Yes, good. So then, yeah, sorry for going a bit over time. Let me stop here. Thank you.
So thank you very, very much. Given that it's like 6:29, I suggest to move the questions later on in the breakout session, breakout room. Okay, cool.
Yes,
And
if
also
you are able to stay, we will have a breakout room right after the next talk for some time, so you can ask questions to both speakers in individual rooms. Thank you for the talk.